Hello. In today's video we're going to be talking about alloys. Just a brief introduction to alloys, what are they, and how are they formed. So an alloy themselves, most people are familiar with alloys. You've come into contact with some sort of alloy in your life. Some examples of this are brass, bronze as well actually, solder or amalgams, steel. All these are examples of alloys. Alloys are a combination of two or more elements, generally metals. So alloys, materials that contain more than one element. And almost always those elements are going to be metals. Just as a note, one of the common ones that is not metal material is going to be stuff like steel. So steel has iron along with carbon, but generally we're talking about two metals. Okay. Alloys are going to take the initial properties of the metals and change them. As you guys hopefully remember from our previous video, if you have a metal, it is very ductile. It is very malleable, but once you start shoving other things in there, it can change the properties. It can make it a little bit more brittle, a little bit more hard. Just depending on what type of properties you're looking for, making alloys with metals can get you some properties that are favorable. For instance, steel is significantly harder than iron by itself. Okay, you can also change melting points and stuff like that. A lot of alloys are called solid solutions. If they are mixtures. We're going to look at an example of what's called an intermetallic compound, which kind of goes under the umbrella of alloys. But it is actually a compound, so not a solution. But this is called a solid solution because we have a solid solute plus a solid solvent, making it a solid solution. The intermetallic compounds themselves, a little bit different. I'll talk about that in just a minute. So here are a couple of examples of common alloys. And they're just going to have different percentages of different metals, again, except for our steel substance, which has the addition of carbon in there as well. And the properties are going to be different from our initial metals that we start out with. So, for instance, iron, we know iron will easily oxidize to iron oxide, but steel actually resists that corrosion. So, just as a note. Okay. Now, let's look at what happens to make an alloy. So we take some combination of metals. So we're going to call them metal A, metal B, and metal C. In this case, A and B are similar in size. C is a different size. And through the alloying process, we can either get a solid solution, getting an interstitial or substitutional alloy, or we can get an intermetallic, which is actually a compound, so not a solid solution, and it's still made by melting metals together. Or we can get a heterogeneous alloy, where we have areas within there that are one phase, and then areas that are a different phase or different substance. So not quite a solid solution because it's not homogeneous, right? It's heterogeneous. So let's look a little bit more at our types. So we have our substitutional, alloy. So one element takes the place of, or a second element takes the place of a metal atom within the pure metal lattice. So we're talking about in the original lattice. Okay. To get a substitutional alloy, you have to have the two metal ions, the initial metal lattice ion and the substituted in metal having similar atomic radii. And remember, these are metals, right? We're talking about metal atoms, not metal ions. Our next is interstitial. And with an interstitial, we have a second element filling in the space, the empty space left over from the initial metal lattice. So anytime we have a collection of atoms, we're not going to have 100% filling of our space, so there'll be leftover empty spaces that additional atoms can come in. We call those interstitial holes. So those smaller elements can fit in the little interstitial holes left over. You can kind of see that here. See how the little atoms, the smaller atoms fit in the spaces left behind. So the solute atoms, as we would call them, have a sufficiently small radius to sit in an interstitial hole in the metal lattice. Okay. Our last one is heterogeneous, or the last real kind of normal type of alloys are heterogeneous. And our components are not dispersed uniformly. So when we add in our solute, it only goes to certain parts of our solution or solvent, metal solvent. So only certain parts will form certain alloys. And we get these a lot when we cool quickly. Okay, and that results in different phases throughout. Okay. The other thing we're going to look at is a intermetallic compound. So now we don't have a mixture, we have an actual compound form. So this will have distinct properties because we have a definite composition. Set that a little bit. Doop, doop, doop. Okay, so let's real quick look at this. So this right here is a diagram that shows you at what temperatures and mole ratios of substances, this graph right here. So we have different compositions of magnesium and lead in this case, and then different temperatures, and we look at what temperatures you can isolate different intermetallic compounds. So they take these substances, they take a combination of different metals, combine them, heat them up at certain temperatures and at certain ratios to get different compounds. So, and different phases of those compounds. And like I said, they will have very specific combinations of those elements, so they will form a compound. So much more similar to a covalent substance versus a metallic substance. I mean, it still has much more metallic type structure, but now we've got set compositions. With alloy, you're just kind of shoving stuff in and you don't have a set. It's still, no matter how good you get those compositions, with our substitutional, interstitial, and heterogeneous alloys, we're not making a exact defined composition of, or molar ratio of elements like we see with our intermetallics. These we just have, if we look back at this, our alloys, our regular alloys, have percentages of elements, but not molar ratios of elements. Okay, so they usually, because this is a compound, are going to have better structural stability and higher melting points than the constituent metals, and they are a compound, so when we look at our covalent network compounds, are a little bit more similar to that. So let's look at our properties. As I said, they'll have better structural stability and higher melting points than the constituent metals. However, now we're dealing with something that has a very set structure throughout, so it's not just like some atoms thrown in randomly, so we're going to have a more brittle substance than a substitutional alloy. Okay. And that's about it. Hope this helped you guys. See you guys later.